Start recording. Well, so far we have seen this kind of configurations where the magnetic field was stationary, B magnetic field was stationary and constant. Stationary and constant, and for example, in first case, our bar was moving with some direction V. This configuration called motional electromotive force. You may remember it. Motional electromotive force. What does it mean? It means that in some magnetic field. Okay, let's look to the configuration A. Our bar moves to, in this case, to the right in some stationary and constant magnetic field. This called and electric motive force, which is induced in this configuration, is called motional electromotive force. Well, there is another possibility where the our loop will stay stationary, but magnetic field, in our case magnetic flux density B, will change with some our magnetic field changes in time. When magnetic field changes in time, we have already seen, due to the Faraday's law, there induces some electric motive force, and this electric motive force called transformer action. Transformer action electric motive force. In transformer action electric motive force, the loop will stay stationary and magnetic field changes in time. Okay, the reason why this is called transformer action EMF is because it is commonly used in transformers. Well, we'll see one problem for this concept also. When magnetic field changes and loop stay stationary. Well, when we discuss stationary circuits, we must use transformer action. Okay, we'll see. Okay, example 10.4. So let me copy this from the book. Example 10.4. 10.3. Well, let's see this example. Sorry. Yes. Okay. So, is it visible to you? Can you read the problem? Well, no answer. I hope yes, you can read. Well, first let's read. A uniform magnetic field is generated by a time-varying source as shown in figure 10.6a. This is so. A stationary loop is placed such that its plane is perpendicular to the magnetic flux density. Okay. Assume the flux density is sinusoidal and given as B equal to B0 sine omega t, with B0 equal to 0.1 Tesla. Omega is 100 p radians per second, and the sides of a square are 0.1 meters. A equal to 0.1, B equal to 0.1 as well. First, calculate the induced electric motive force in the loop. Okay. According to the Faraday's law, induced electric motive force in the loop was minus the magnetic flux over the T, and this was equal to magnetic flux phi m was integral of b ds, and we put this to our first equation, and electric motive force will be equal to minus the T, okay, b ds, and which is equal integral over the surface S, which will be equal sorry so the magnetic flux is varying with time, that's why we take the derivative of b with respect to time, and we multiply by S, which is the surface area of our contour, and b is given as b0 sine omega t, and if we take from b the derivative with time, we will get. Okay, let me open a new page. So B was given as B0 sine omega t, and it means that the B over the t is equal to B0 omega from, okay, sine is cosine omega t. That's why the electric motive force will be minus B0 omega cosine omega t, everything multiplied by s. Or, okay, let's write in this way: B0 omega s cosine omega t, in order not to confuse you. Well, as we said, the surface of our square, which is a multiplied by b, we replace it. So b0 omega a b cosine omega t, and is equal to okay, b0 was 0.1 multiplied, omega was 100 p radians per second, yeah, 100 sorry, 100 p. A is 0.1, B is 0.1, 0.1, 0.1 multiplied cosine 100 p t. And this equals to, okay, 0.1, 0.1, and 0.1 and 100 simplifies, and this will be equal to 0.314 cosine 100 pt volts. As we can see, now in this case the electric motive force is AC, and in this case we have seen the working principle of AC generator. Now, if we move to the second part of our problem, let's see previous slide here, part B. What is the induced EMF in the loop is made of 100 turns placed essentially the same location. No, cancel. So well, B, part B. Now we have 100 turns, n equal to 100 turns. At the very beginning we have seen that if we have n turns, EMF was equal to minus n multiplied the phi magnetic flux over the t. This we have already found is equal to 0.314 cosine omega t. This is 100, and induced EMF in case of 100 turns equals to minus 31.4 cosine omega t volts, with maximum values of plus and minus of 31.4 volts. These are the maximum values of our induced EMF. If we look, you will see the pure sinusoid with the maximum values of minus 31.4 and plus 31.4 volts. Okay. The third part of our problem, the C. What is the solution in A and B if the loop is at angle alpha to the field, as shown in figure 10.6 C? Okay, if we look here, our loop is not perpendicular to the magnetic flux, but it is at some angle alpha with the magnetic flux. Now, what will be the electric motive force in this case? Well, the solution is in this case also similar to the previous cases, to the case of A and B, but the only difference in our case, the dot product between B and DS in the case C here, dot product between the, okay, this is, well, these are the vectors of B, this is the vector of DS, as you can see, and dot product between these two, if we look, okay, equals to B multiplied S multiplied sine of yes, 90 minus alpha. No, sorry. Cosine of 90 minus alpha. Yes, because we are dealing with dot product. So dot product between B and D is B multiplied okay ds surface multiplied by cosine of 90° minus alpha, or is b multiplied ds sine alpha. And we put directly to the equation of EMF, electric motive force, which was no, it was here, yeah. So our EMF was minus omega B0 B0 cosine omega t multiplied sine alpha multiplied to integral of ds over s. And we have minus omega B0 integral of ds over s gives us s, which is surface, minus omega B0 s minus omega B0 s sine alpha multiplied cosine omega t, which is simply equal to minus 0.314 sine alpha cosine omega t, where omega is equal to 100p. And in the case of 100 turns, EMF becomes similarly minus 31.4 sine alpha cosine omega t. Okay. Well, so far, do you have questions or problems with understanding? Okay, why you are only 2? Okay, let's move on in this case. Well, we have seen the separately motional electromotive force and transformer action electromotive force. Well, what happens in the case when we have combined case? It means if we look to this configuration, for example, to this picture, if we look to this picture, what happens in the case when we have both varying magnetic field and also our loop is, for example, rotating with some angular velocity, no, with some angular velocity. In that case, we use combined motional and transformer action electromotive force concept. Well, so motion action electromotive force was electromotive force equals to integral over the closed path C V cross B by D, okay, DL or DR, doesn't matter, let's say DR. And the transformer action EMF was general case with n turns, n multiplied the phi over the t, the phi m, magnetic flux. Okay, in the case of combination of motion action and transformer action, or in other words, if our contour is both our contour is moving and the magnetic field is changing, what will happen? The combinational electric motive force will be just the sum of these two, or the integral over the closed path C V cross B multiplied, we said dr. Okay, dr minus n the phi m over the t, or if we write in terms of magnetic flux density and so on, equals to C V cross B dr minus n the B the T multiplied ds, the integration over the surface S. In this case, I replaced this with this, or more clearly, Fm was replaced by this integral. Okay, this is this expression is more general expression of Faraday's law. Okay, now we'll see one problem. Okay, before that, let's do a reconnection because we are soon out of time. Let's do a reconnection. So I will resume recording. Okay, it's going. Well, we have seen we have derived the general expression of Faraday's law, and let's see the application of this equation or this expression. Well, let's move to our book and let's see. Let's take this case. Let's take into account this case. Okay, I move it here. So consider the situation shown in the figure. The loop rotates around the axis in a constant uniform magnetic field at angular velocity of omega. Okay, it rotates with angular velocity of omega. At any given time, the normal to the loop surface is, okay, is ds. This is the normal to the loop surface. At any given time, normal to the loop surface makes an angle alpha. Here is alpha with magnetic field. Since magnetic flux density is constant in time, there is no electric motive force due to the change of flux transformer action. Well, first we take into account that B is constant and transformer action EMF is 0. We have only motion action EMF. Okay, since the loop is rotating and each section of loop moves at some velocity v, there exists some induced EMF due to the motion. Okay, motional action EMF in our case. Sorry, I will write with black. Motional action EMF in this case is equal to the EMF of each side of the loop of AD no A AB BC CD and DA. EMF of the side of AB plus electric motive force of the side of BC plus electric motive force of the side of CD plus electric motive force of the side of DA. Now, electric motive force in the section of BC, in the sections of BC and DA, this and this are 0. Why? We have seen in previous lesson, because for the sections BC and DA, the cross product of the we have vector dr for each side, and we have cross product of V cross B. For these two sides, dr and V cross B are perpendicular. That's why if they are perpendicular, their dot product will be 0, because cosine of 90 degree is 0, and it means we have only the electric motive force because of section AB and CD. So now, in order to compute electric motive force in these sections, we have to find velocity vectors in these sections. So velocity vector in AB is equal to if we look to this second picture, the velocity here equal to r multiplied by omega. It comes from geometry, and r multiplied by omega, and we add vectors as well, cosine alpha minus y sine alpha, and similarly V CD equals, again, that distance is r, and angular velocity is omega, r omega, and vector is opposite from VAB, and it means minus x cosine alpha plus y sine alpha. Now let's compute the cross products of V cross B for each section. For the section AB, V AB cross B. Okay, if we go back to our problem, you may see that B, magnetic flux, magnetic field lines coincide with the x-axis. It means B here, magnetic flux density B is equal to x multiplied B0. Okay, B0 is here the magnitude of magnetic flux density. And VAB is equal to R omega x cosine alpha minus y sine alpha. So let's write it here. R omega x cosine alpha x cos alpha minus y sine alpha cross x B0. It equals, okay, when we multiply x cross x, unit vector x cross product with unit vector x gives us 0. That's why remains only what? Remains only minus y cross x multiplied by r omega B0. Minus y cross x gives us z r omega B0. Sorry, we forgot about sine alpha multiplied sine alpha and is equal to z r omega B0 sine alpha. Similarly, the cross product of VCD cross B equals to minus z r omega B0 sine alpha. And now the total EMF is equals to V cross B by dr over the closed path C. This is so this is what? This is from A to B, VAB cross B dr plus from C to D again VCD cross B dr. Okay, we already know the values of these cross products, and this integration gives us okay B0 RH, where H is the distance between A and the B, sorry, B R H omega sine alpha, and okay twice. So please don't confuse this C with the answer. And it gives us electric motive force equal to B multiplied to R multiplied H multiplied by omega multiplied by sine alpha, where 2r multiplied by h is equal to the S surface of our contour and is equal to here B0. Don't forget, because this is the magnitude. S multiplied by B0 multiplied by omega sine alpha. Okay, here one more thing, we need to denote alpha. Alpha is equal to omega, the omega multiplied by time, and electric motive force will be equal to S by B0 omega sine omega t. Well, this is the electric motive force of the closed path rotating in a constant magnetic field with angular velocity of omega. And in case of, if we have n turns, the electric motive force becomes S B0 N omega sine omega t. Okay, this is the electric motive force for rotating contour in a stationary magnetic field. And you can see here the electric motive force again is producing alternating current, not direct current but alternating current. Well, we came up to here. For today, I think this is I hope this is enough. Tomorrow we will see the combination of motional and transformer action electromotive forces. It means here, yes. It means here we have the now in our problem the magnetic field was stationary. Tomorrow we will see what happens if both magnetic field changes with time and our closed contour rotates along some axis. Okay, for today that's it. You are welcome. See you tomorrow. I will stop the